Alright, so we want to prove that being able to integrate a function is equivalent to being able to integrate the function restricted to any rectangle that's part of a partition, and that integrating the function over the entire rectangle is the same as integrating the function over each element of each rectangle in the partition and summing those together. Okay, so we first want to prove the if and only if. So let's see here. So for each subrectangle, f restricted to s is integrable. Okay, so I think this is supposed to be proving it for every rectangle s in the partition P, but we're going to prove this direction for any subrectangle of A. So let S be any subrectangle of A. Let epsilon be greater than 0. So we want to prove that f restricted to s is 0 is integrable. So we want to prove that we want to find a partition such that the upper sum of f restricted to s at this partition minus the lower sum of f restricted to s at this partition, that difference is less than epsilon. So let epsilon be greater than 0. Since f is integrable on A, let P prime be a partition of A such that UFP prime minus LFP prime is less than epsilon. We need integrability to guarantee the existence of such a partition. Now let P double prime be a partition obtained by taking the rectangles in P prime and intersecting them with both S and the complement of S and A. Okay, so what we're doing is we're basically taking this partition P prime and breaking up the rectangles further to guarantee that we have a subset of these rectangles which form a partition of S. Okay. Then we have epsilon is greater than, of course, it's greater than U F P prime minus L F P prime. And now P double prime is a subpartition of P prime because because we get P double prime by taking rectangles in P prime and potentially breaking them up further. Oh, by the way, so when I say that we take P prime and intersect them with both S and A set minus S, I guess you can't really just do that alone because you might get weird looking sets that don't look like rectangles. You have to take these intersections and potentially break them up even further so that you get rectangles, but that doesn't really matter. What matters is that you get rectangles. What matters is that you get a subpartition of P prime which contains a partition of S. That's really what we want. And I'm just showing that that can be done. But anyways, P double prime is a subpartition of P prime, and so the difference between the upper and lower sums is even better. So this is greater than or equal to U F P double prime minus L F P double prime. Okay. So now, so this is of course equal to the sum over all rectangles in P double prime of, so the upper sums we're going to take MRF And for the lower sums, we're going to take lowercase mrf times VR. And the reason I've written it like this is because basically the upper and lower sums are like distinct sums, but because each term contains a factor of VR, we can factor them together and write it like this. So anyways, so this sum is over all rectangles in P double prime. Now some of these rectangles are subrectangles of S, and some of them are subrectangles of A set minus S. And by the way, we're not really going to worry about the edges of the rectangles. Yeah, just don't worry about it. I guess technically you have to worry about them, but I guess you could, if you really wanted to, you could go ahead and prove that, like, if you were so what could you go ahead and prove? Like, you can define the same things. You can define these, instead of using closed rectangles for our partitions, you could use open rectangles and sort of get the same thing as long as you eventually cover everything. So you might have to use a combination of closed and open rectangles. But the point is, like, that those boundaries of the rectangles can be covered by arbitrarily fine, or by the edges themselves can be covered by rectangles of arbitrarily small volume, and so in the end they don't matter. So anyways, with the exception of the potential confusion at the boundary, we have rectangles in this double partition which are either in S or not in S. So we'll break the sum up into the ones which are in S. So the sum over all rectangles in S, MRF minus MRF, of course upper and then lowercase. And then we add the rectangles which are not in S. But wait, let's think about this. So right, so the sum over all rectangles not in S, then I'm just going to put a dot because it's literally the same thing. So now if we get rid of the sum over all rectangles not in S, then we're dropping out a whole bunch of potentially positive terms, and so the sum gets smaller. So this is greater than or equal to the sum over all rectangles which are contained in S of, again, the same thing. But then this can be written as UF. Now, because we're considering only the rectangles in S, we can now replace F with F restricted to S, because we're only taking the sum over rectangles which are contained in S. And this partition, we're going to call it P double prime restricted to S. So this is P double prime, but you only look at the rectangles which are contained in S. So it's this upper sum minus this lower sum, F restricted to S, P double prime restricted to S. Okay, so given epsilon greater than 0, we have found a partition P double prime restricted to S. This is a partition of S such that the upper sum of F restricted to S minus the lower sum of F restricted to S is less than epsilon. And such a partition exists for all epsilon greater than 0. And so what that tells us is that F restricted to S is integrable. And that holds for any subrectangle S of A. And so that's one direction. Okay, good. So now we need to do the other direction. Conversely, suppose Now here we're supposing that f restricted to S is integrable not for every single subrectangle S of A, but for every single rectangle S which is contained in the particular partition P that was chosen in, or that was given to us in the problem statement. And given epsilon greater than 0, if we write, so we've got a partition. Are partitions always finite? I believe they are, but let me check this. I'm not 100% sure. I forget. Come on, Spivak. Please load. I'm pretty sure it has to be finite. Or at least, even if it was defined for potentially infinite sums, you could get arbitrarily close to the infinite sums by considering finite sums. And in fact, yeah, that's exactly what we do. We take supremums and infimums. So even if you just define it for finite sums, you eventually can get to infinite sums when you take the infimums and supremums. That's taking a while to load, actually. Let's just assume, for now, that it works. Okay, so given epsilon greater than 0, if we write P to be a partition consisting of rectangles S1 through SM, so we've basically just enumerated the rectangles, then for each SI, there is a partition PI of SI such that we take the upper sum of F restricted to SI with respect to the partition PI, and we subtract the lower sum of F restricted to SI. But then this is going to be, we can make this less than any epsilon that we want. And that's possible because F is integrable. Here we're going to choose epsilon over M because that happens to be the value that we need. Okay, here we go. Let's look at this thing. Yeah. It's a collection of P1 through Pn. So it is indeed finite. Okay, cool. So it's less than or equal to, so this, find a partition that will give us less than epsilon over M. And we basically just put them together. So let P prime be the partition consisting of all the partitions, P1 through Pm. Then certainly P prime is a partition of A. Furthermore, if we look at the upper sum, P prime, we subtract the lower sum, F P prime. So this is going to be the sum, again, just by definition, this is sum over all rectangles in P prime, MR F minus lowercase mr F times VR. But because P prime consists of the partitions P1 through Pn, and these are partitions of disjoint sets, this is precisely, here I'll continue the equal sign over here, this is precisely the sum, you can sum from I equals 1 to m, and then do the sum over all rectangles in each particular partition Pi of MR F minus MRF times VR. Okay, so now what we can do, this sum on the inside here is taken over all rectangles R which are in the partition PI. So each rectangle is a subset of SI. So when we're taking the MRFs, we're only taking a supremum over a subset of S. So we can take F and restrict it to SI and get the same value because we're not changing anything. Times VR. But now if we look at this by definition is precisely the upper sum of F restricted to SI with respect to the partition PI minus L F restricted to SI PI. So then this is, of course, each of these upper sums minus lower sums is less than epsilon over m by the choice of the partition PI. So this is less than sum from I equals 1 to m of epsilon over m, and so we just take that constant multiplied by m and we get epsilon. Thus, f is integrable on A. Okay, so f is integrable on A if and only if it's integrable, only if its restriction to any subrectangle of a particular partition is integrable. Then lastly, by linearity, which is exercise 3-3b, specifically, we look at the integral over A of f, assuming that it's integrable. Now f is precisely the integral over A of the sum over all rectangles S of f restricted to S. Now, this is assuming that all the S's are disjoint, which if we're using closed rectangles, they technically aren't. They technically overlap at the boundaries of the rectangles, potentially, but again, as I alluded to earlier, we really don't care, and I don't want to go through the trouble of explaining why we don't care. It's too tedious and it doesn't really give us much benefit. So anyways, we have an integral of a finite sum. So basically, 3-3b tells us that an integral of a sum of two things is equal to the sum of the integral of the two things. So basically, integrals will commute with one sum. Now, anytime you have a result like this, you can extend it to finitely many sums just by using induction. So if you have an integral of the sum of functions f1 through fn, then that's equal to the integral of the sum of the integral of f1 through the integral of fn. That's just a standard thing you do in math. Whenever you prove something about an operation that you can perform on two things, you can perform it on finitely many things, typically. So anyways, by extending linearity to finite sums, we can bring this sum outside. So this is the sum over all S, the integral over A of f restricted to S. But if we're taking f restricted to S and integrating it over A, f restricted to S is going to be 0 outside of S. And so integrating it over A is the same as integrating it over S, because if you integrate this function on A set minus S, well, f restricted to S is going to be 0 on that set. So this is the same thing as this. Okay, so there we go. And that shows us basically that being able to integrate on one rectangle is the same as being able to integrate on subrectangles. And that's useful to know. It should sort of make sense, because if it weren't true, then you could look at if you had an issue integrating on a subrectangle, then you wouldn't be able to get the difference between the upper and lower sums to be small enough there, and so you couldn't get it small enough everywhere. So it sort of makes sense intuitively that this would be the case. But yeah, that's about it for this exercise.